And number 21, you are being asked to, just checking here to see, it says, calculate the value of K for this reaction at this temperature. So you're given, I'm going to find a little bit different color. Oh, a highlighter ought to work really well here. You're given that NO has this equilibrium concentration. Now these are all gases, remember. That is important to remember, that in this problem all of these things are gases, and that will become important as we continue to work here. But the concentration of the hydrogen gas is given. The concentration of the nitrogen gas is given. Concentration of the water is given. So the first thing we do is write down the equilibrium expression. Then we substitute in the concentration of nitrogen and the concentration of water and the concentration of NO and the concentration of hydrogen gas. Hopefully I said nitrogen back up here with the 5.3 times 10 to the 2. And then we solve this. Now, here's a case where you really want to practice putting this into your calculator and get very good at how your calculator works, because some of you are going to put this expression right and all of this part up here will be right, but you'll get this wrong because you didn't put it into your calculator correctly. So check that in problem number 21. And problem number 22 is very similar. It just says calculate K for this temperature. And once again, it's important to note that in this problem all of these are gases, and the gases are together making a solution of gases dissolved in gases. And here in problem number 22, though, we are calculating just plain K. We are given the concentrations in molarity. So write down the equilibrium expression, NCl3 squared divided by, and the concentration of nitrogen gas, and divided by the concentration of chlorine gas, cubed, because the coefficient up here is 3. So the chlorine gas is cubed. So just substitute those values in, and you calculate the equilibrium constant. Number 23. The only new and tricky thing here in number 23 is, remember, we're working with calculations. Of course, also don't forget that once again, these are all gases. They're all in the same phase. They're all in the gas phase. And here we were given the moles, and it's in a 3-liter container. So to calculate the molarity, you had to divide the moles by the volume. And that's what goes into the equilibrium expression to calculate Kc. So be sure you calculate that for number 23. Question number 24, we spent a little bit more time going over in class together. Now in problem number 24, you're given some original original moles in a 2-liter container, and you're told this is at equilibrium. So from that, you use the equilibrium expression and you substitute in your values so that you calculate Kc, the equilibrium constant, and this equilibrium constant comes up to be 4.08 times 10 to the 8. Once again, some of you are going to be in trouble if you don't practice calculating that and make sure you can get that. Now, that's not the answer to the question, is it? Now it's time to answer the question. Of course, you can't do that if you don't know what the question is. The question is here it is, given the initial concentration in the problem, given a new set of initial concentrations. I kind of added that word because this is a system of initial concentrations that we're being given. Tell if the system's at equilibrium. Is it at equilibrium? That's the question right there. Is it at its equilibrium? Well, to do that, to answer that, we're going to find Q, the reaction quotient. Now Q, you see down here, has the same form as the equilibrium expression. You'll see they look exactly the same. We're just going to substitute in these initial concentrations that we were given and calculate Q. Well, Q came up to be 4.08 times 10 to the 8. Those things right here, they're the same. And if those are the same, if Kc and Q are equal, the system is at equilibrium. So here we have the answer circled in red. I mean, like, I could highlight it here, but then how could we tell the answer? Everything on this page is highlighted. Okay, well, we could get rid of some of those other highlights. Anyhow, you know what the right answer is, and you put it in some kind of box so other people could tell as well. Moving on to number 25. That's how number 25 gets set up so that you can maybe be sure you're getting that part. 26. There's the, oh, look what I did here. This is something you have to look out for. Did I write Kp? This is the equilibrium expression in terms of pressure. So this needs to be Kp is 3.8 times 10 to the 4. Now, answer the question. At the initial concentrations given, will the system be at equilibrium? So, you use the equilibrium expression, and into the equilibrium expression, you substitute the values given in the problem for partial pressures of the different gases that are involved, and you should get this for Q. Now, this system is not at equilibrium because Q does not equal C. Q does not equal the equilibrium constant. And once again, it looks like I should have put this in terms of pressure. I just didn't notice that as I was working on it earlier, that those are in terms of pressure. Now this problem, that's all it's asking you to do is tell if this is at equilibrium or not. And all you need to say is the system is not at equilibrium because Q is not equal to K. So we've worked a little bit here with equilibrium expressions involving pressure, so we probably won't go over that here in this video. Well, let's take a look at it. Kp is solubility in terms of partial pressure of the gases. The Kp expression is the same as the concentration. Now they are related. They are related. If you know Kp, you can calculate Kc, where this is the ideal gas law. This is temperature in Kelvin, and this is the change in number of moles of gas in the reaction.